In our last video, we discussed about the binary operation, which actually representing the closeness of a set. Now, in this lecture, we will discuss about the semigroup and the monoid and their properties, and also go through some examples. So, starting from the binary operation, uh, a binary operation that we already discussed in our last video. A binary operation is a rule for combining exactly two elements to produce a single new element. And formally, a binary operation combines two elements taken from a specific set and maps to the result back into the same set. So we can express the binary operation like this. Let's say star. When I am just trying to revise it, S is a non-empty set. S not equal to 5. Okay, and like this, if A B belongs to S, then star A comma B that was going to A star B. Okay, where A B belongs to S. So now that was the binary operation we already discussed in our last video. So now we will try to extend this property. Okay, we will include one more property in the binary operation. Later, if the binary operation is associative, okay, then what will happen? Okay, let's try to record it. If a binary operation is associative, then actually we can write it mathematically. Let's say S is a non-empty set, okay, and let's say star is a binary operation, okay. Now this star is called associative, okay. Star is called associative if the following equality holds, okay, okay. So let me write the equality. So this equality holds. Now if star, so I am trying to tell you what is happening here. Actually in general we know that what is the definition of associativity. If let's say ABC belongs to G, then ABC, then G is associative if these kind of things happen for addition, let's say. Okay, generally we know this. I mean, I am writing not in math, in I'm roughly writing this. Okay, this kind of thing, but there is a loophole in this definition. Okay, let's say 1 2 3 belongs to R. Okay, this is R is a group under addition. Okay, so under close under addition. So if we say that in that case R is associative, that's no doubt about it. But the problem here is that there is no order in the elements. Okay, according to this definition, okay, in this definition we can write the associative law like this. Right, the associative law, like, I mean, for this way, all the things are, I mean, if I am telling that 1 2 3 belongs to R, then actually what I am trying to say, which pair, okay, and many other pairs also possible in that case, but which pair I am trying to say, there is no guarantee in that case. So that is a bit loophole in this definition. So better you write like this. I mean, the order will be remain same for if you take the order triplet. Same. I mean, this is looks like difficult example, difficult. But if you go through this definition, you will see that this is just I am taking the order triplet from S cross S cross S. Let's say S is a non-empty set. Okay, and star is a binary operation. We are just taking an order triplet A B C. So that we cannot change the order. Okay, if some element is 1 A cross B cross C, A comma B comma C belongs to S cross S, then we can just first of all the associative law, okay, we just take the bracket in the first two S, okay, and leave this S alone like this. Okay, so if you go through this example definition, I think you will be able to understand what I am trying to say. And actually just we are trying to take the order triplet, nothing else. Everything is same in the definition. Okay, so now this is the definition mathematically. Okay, otherwise everything is same. And uh, now we saw that star is a binary operation with associative law. Okay, they what this call actually. So just we add one more property in the binary operation. Okay, so this is called the semigroup. Okay, a binary operation with associative law is called the semigroup. Now we will go through some examples and some properties of semigroup. Okay, first of all, let's see some examples of a semigroup. Let us take first example. Let us take the natural number under multiplication. Okay, the natural number under multiplication. So First of all, just we already actually go through this example. So this is very much clear that this is closer. Okay, n cross n. Okay, under multiplication. Okay, this is a binary operation. That means this is close. I mean, the product is close. Okay, and also this is associative. Okay, this is also very much trivial because we know that if a b c belongs to n, then this happen. Okay, see, this result holds for natural numbers. Okay, so we already go through this thing. Okay, so natural number under multiplication is associated, is a semigroup. Is there has any identity in natural number? There doesn't has any identity because yes, there is identity. One belongs to n. Okay, so identity is there, but no inverse. There does not exist any inverse. Okay, so yeah, this is a semigroup, but yeah, there is identity. That's another thing, but this is a semigroup. We can say that n under multiplication is semigroup. Okay, similarly q under multiplication is a semigroup, also a semigroup. Okay, so now let us take an example which is not a semigroup. Okay, we already go through such example in our last class. Now another taking another example, an interesting example. Let's say n cross n star is an operation, n cross n to n, and we are defining star as, okay, just a b, and where a b belongs to n. Okay, and this is an operation, an interesting one. Okay, a to the power b, we are defining the operation like this. Okay, so is it associative? This is, I mean, we can clearly say that this is a close, this is a binary operation. Okay, because if we take any two of numbers, let's say 2 and 1. Okay, these are belongs to n. Okay, and 2 to the power 1 equal to 2, that means this is also belongs to n. So okay, no, just, I mean, example is not the proof, but yes, we know, it is obvious that this will going to be a natural number, because negative number cannot possible for if we taking on the positive numbers. Okay, just we dealing with the positive numbers also. But is it associative? So this is the most important thing that you need to check. So let's see this is associative or not. Let us take this example. 3 to 1 belongs to n cross n cross n. I mean, I am writing the associativity in the order. Okay, in like the last example, I mean, that I already saw in the definition. Now let's say star, I mean, just applying the operation here. Okay, star 3 to the power 1, that's mean 2 to the power 1. Okay, and star 2 to the power 1, that's mean 2. And according to the definition, 3 to 3 square, that's mean 9. Okay, and now in this case, okay, first of all, this 3 square, that's mean this is 3 square and 1. Okay, so star 9 comma 1, 9 to the power 1 equal to 9. So this 3 to 1 actually holding the associative law. Now let us take another example. Is it associative? So now let us take another example. Let's say 2 3 4, which is also random number, randomly taking. Okay, this is also belongs to this. Okay, now let us see this is associative or not. So this is going to be 3 star 3 to the power 4, that's mean 81, and 2 to the power 81. Okay, I am not calculating this. Now again, 2 comma 3 comma 4. Okay, this is going to be 2 to the power 3, that's mean 2 to the power 3 comma 4, that's mean uh, this is 8 comma 4, and this is 8 to the power 4, which is going to be 2 cube, that's mean 12. Okay, so yeah, you can clearly see that this is 2 to the power 81 and this is 2 to the power 12. So these are not equal, so associative property is not holding for 2 3 4 in that case. This one, if this is not working for you, then you can also try this same for this opportunity. This is also closed. Okay, and not associative. Okay, so yeah, this one. Now let's say another example. So no more examples. I think these examples are enough. I will discuss more examples in further lectures. I am not willing to give all the examples at once. Okay, I am trying to give all the examples step by step. Okay, in throughout my lectures, in throughout my lectures you will see lot of other examples. Okay, so now let's go through some properties. Actually, what actually a semigroup is convey. Okay, let's say G is a semigroup. Okay, that means G is closer as well as G is associative. Okay, under some operation star. Okay, now what property G will have? Okay, first of all, G will convey a lot of properties, but in this case I am telling you just the basic properties. This one plus n. Okay, where m n belongs to natural number. Okay, so be concentrated. M and n not equal to 0. M and n belongs to natural number. It will go from 1. M and n cannot be 0. Okay, and one more property, uh, this one. Okay, there also M and n belongs to natural number. Okay, so notice that natural number, not z or not whole numbers. This is not, M and n cannot be equal to 0. Okay, M n not equal to 0 in this case also. M n not equal to 0. Okay, so now, uh, this look like very much obvious results for you, I think, but these results are not obvious because we are dealing with group G. Okay, in R, if A belongs to R, that for this case we already, I mean, go through this kind of properties. Okay, we know this from our very childhood. Okay, but then is a obvious question that comes to our mind, that now why we are trying to prove this easy properties, because we are not dealing with now R, we are now in G. That's in generalize whatever group, whatever set. Okay, the set, let's say S, this is close, and let's say associative. Okay, if any set is close and associative, that's mean this set will going to convey these properties, these two properties. Okay, so this is the most important thing that we need to understand in that case. Okay, till now we are discussing, we are in the R only, but this time we are not in R, we are in G, a group where a semigroup which conveying the property closeness and associativity. Okay, so for this, if any set conveying these two properties, that's mean they are going to convey these results also. Okay, this is the thing that I want to tell you here. Now, another thing that is very much important to understand here is that, now, one question that comes to our mind, that what is the advantage of having some semigroup? Okay, what is the advantage of having such properties for a semigroup? Okay, so let us go through an example, real life example. Let's say you have your kingdom. Okay, and some unknown enemy is going to attack to your kingdom, but you already somehow managed to know that this enemy is a semigroup. Okay, then you will just go to your notebook and just try to find the weaknesses of the enemy, and these weaknesses are these properties. Okay, that's mean, let's try to figure out this. That's mean, just by knowing that a set is semigroup. Okay, if you are dealing with some unknown set, and if someone managed to know that this set is a semigroup. Okay, then we can apply these two properties without thinking, because we already proved these properties for all semigroups. Okay, we in general we prove it. Then if we have some particular set and we already proved that this set is a semigroup, then we can apply these two properties. This is the advantage of deriving the results. Okay, so now let's try to prove these properties. Okay, I will just prove for one property, the first one, and I think you will be able to prove this for the second one also, just similarly. Okay, so let's try to prove it for let's try to prove this one. Okay, so we have a to the power m into a to the power n equal to a to the power m plus n. Okay, so this is the operation of G. Okay, star operation, you can say it like this. Okay, so now, one thing that I want to tell you here is that a star like this, let's say m number of stars. Okay, this is going to be a to the power m, we write it like this. Okay, uh, this is in symbol notation. Okay, now let's say n equal to 1, because we are in natural number, so natural number start with 1, and we are proving it with the in process of induction. Okay, that's mean a star a equal to a square in that case. Okay, this is the notation. Just try to remember, if we have just operating the same element again and again, we can just keep the power in the index. Okay, so this is the thing. Now let's say n equal to 1, then okay, then m star a 1, so this is going to be a, and that's been using this property. Okay, we are just multiplying a with the a to the power m, that's mean m plus 1. Okay, so this is true for n equal to 1, that's mean this result is true for n equal to 1. Now just like how we do the induction process, this is true for n equal to k, that's mean, therefore we can write it like this. Okay, a to the power k, this is true for this, that's mean a to the power m plus k. Then we have to show that this result is true for k plus 1. Okay, so that's mean, now we can write it like this. mm, a to the power k star a. Okay, from this property, now just using the associative law. Okay, here we can give the bracket. Okay, this is because these are equal, so we can give the bracket here. Okay, as this is associative, we can do this also as the set is associative. Now we already proved that already taken that this is true. So h power k plus 1 star a. Now using this as this is true for 1, so just we can for m, so this, so I can write this. Okay, so from the induction we can prove that, we already proved that this is equal to this. Okay, for all m n belongs to n. Okay, I think you will be able to prove the same for this property also. Okay, similarly, so this is the thing that I wanted to tell you here. This is the proof. Okay, so please go through this and try to understand it. Okay, now proceeding forward, now one more thing that is very much important to understand is that, okay, let's say a semi group, let's say G is a semi group. Okay, that's mean G is closer and as well as G maintaining the associativity under some operation star. Okay, now let's say an identity E, let's say E identity belongs to G. Okay, then we will try to prove that if an identity is in G, that's mean let's say A belongs to G. Okay, A star E equal to E star A equal to A. Okay, so this is going to be the result. So now our motive is to prove that a semi group, okay, a semi group, if this has an identity, this identity is unique. This is our motivation. This is the thing I am telling you. Okay, so let's say G star, okay, semi group. Okay, and this has identity. Someone told us that this is identity. G has identity, let's say. Yeah, so maybe there are one or two or three identities. Let's say there are two identities, E1 and E2 belongs to G. Okay, so that if A belongs to G, A E1, A E1, that's mean A star E1. Okay, I'm just writing it shortcut. A. Okay, for all A belongs to G. Oh, equal to A. Okay, and A E2 equal to E2A equal to A. And this is also for all belongs to G. Okay, so this is the thing. As both A1 and E1 and E2 are identity, so this property will hold. Okay, now what if we compose E1 and E2 together? I mean, this operation is like this, star. Okay, G cross G to G. Ultimately, A comma B is going to A star B. Okay, where A B belongs to G. Okay, this is the thing. Now, E1 and E2 both are belongs to G. Okay, E1 and E2 both are belongs to G. That's mean star E1 E2. This will that's mean E1 star E2. Now, if we consider E1 as the identity, okay, that's mean we will end up with E2. Okay, so I am writing it there if we consider E1 as identity. Okay, so now if we do similar for this, okay, so this will like this. Now, if we consider E1, that's my mistake. If we consider E1, if we consider E2 as identity now, okay, that's mean this is going to be E1. Okay, if we consider E2 as an identity. Okay, that's mean, can you see this is a function? I already told you that the binary operation is a function. Okay, and if E1 E2 are not same, that's mean star is going to, okay, sorry, I made a mistake here. Actually, this is not going to be this. Let's say star again E1 star comma E2. This is also going to map E1 star E2. Okay, now let's say E1 same. If we consider E2 as an identity, okay, I made a mistake here. So can you see that star is a function? Okay, and both are composing a same. For a function, we know that a function cannot map a same number, a same thing to two different things. This is not the property of a function. So E1 E2 here is also this is actually mapping to E2, and here also E1 E2 this is mapping to E1. So that's mean two different things. Okay, that's mean either E1 E2, that's mean the only thing we are left with that E1 E2 are equal. Okay, that's mean if there, that's mean in a semi group, if there is identity in a semi group, the semi group means close and associative property. And in a semi group, if there is any identity, okay, that's mean this identity is going to be unique. We prove it. Okay, because if this is not unique, okay, if these are different, then the same thing same element is going to map two different elements. Okay, so two different elements, which is a contradiction. So ultimately we end up with that. If in a semi group there is a identity, this identity is must be unique in this semi group. Okay, now here I am going to give you the definition of the monoid. Okay, so a monoid is called a semi group. A semi group is called a monoid if the semi group contains an identity. Okay, that's mean is obviously I mean this, if this is called contain an identity semi group, that means this is also unique. So I don't need to tell the uniqueness individual separately. Okay, so that's mean we already which is monoid. Monoid is a semi group. A semi group G is called monoid. Okay, if G contain an identity. Okay, so this is the thing, this is the all definition of a monoid. Now I will end this lecture giving you an example of monoid, and I will tell you other properties. Okay, and some examples also in my last in the next video. Okay, so let me give you an example. Let us take this example. Let S contain 1 2 3 4 5 6 till 12. Okay, and I am giving you the bar in the why this is I am doing. Actually this is not simple 1 2 3. I mean I am defining the operation like that. Let's say as a clock. Okay, we know that in a clock. Okay, if 12 plus 1, okay, is going to, sorry, let's say 11 plus 1 2, this is not going to be 13. This is going to be 13, but ultimately this is going to return 1. Okay, so you can, I think you will able to understand how I am defining the operation. This is like a clock. I mean ultimately after 12 this is again going to be 1 2 3 4 5 like this. Okay, so let's say uh, 11 plus 5, what will be the this is actually 16 in 12, in this is going to be 4. Okay, that is ultimately 4 is going to be here. So now we are defining this as multiplication. Let's say this is multiplication. Okay, in multi, let's say 2 into, okay, 2 into, let's say 7. Okay, 2 and 7 both are belongs to here, so 7 into 2 14, that's mean 2. Okay, so this is going to be in this set. That's mean we are clearly, we can see that this is closed. Okay, and this is also associative, you know, this is also associative. Okay, clearly actually I think by the multiplicative law you can check it. I mean this is obvious, pretty much obvious. Now this is also identity. Okay, 1 into 1 is the identity. 1 into 7, let's say. Okay, that means this is going to return 7. 12 into 1 is also going to return 12, or let's say 7 into 1. Okay, so I did left identity, I mean both sided identity, there exist both sided identity 1, and this also closed, S is closed, and S is also associative. But is S has inverse? I don't know. We will discuss it in our next lecture, and this is a very much important example. Okay, that we will going to discuss in our in further lectures. Okay, in detail. But this is an example of monoid. Okay, that I wanted to tell you, and you can see that one is the only identity here. Is the only unique identity. I mean, you multiply any other number. Okay, you don't going to return the same number again. Okay, one is the only unique identity here. And this is a monoid. This is a monoid. Okay, in this case. Okay, and this is a very much important example. And how star is defined, I don't define star properly. I only told you that this is like the, you know, the clock, but we will define it in mathematically. We cannot say that this is like the clock. Okay, we have to define the star mathematically, so I will define it in my further lectures, so please stay tuned. So for this video this is all. Thank you.